welcome everybody, and thank you for coming to Strait Science. Strait Science is a public evening science presentation series put on by UAF Northwest Campus here in Nome, and also UAF Alaska Sea Grant. And this, again, we're in the home office for this time being. And UAF Northwest Campus and Alaska Sea Grant, we are public servants for the Bering Strait region, which is the homeland and waters of the Yupik, Inupiaq, and St. Lawrence Island Yupik peoples. And tonight, it's the drones. Drones are around in Nome, and you do occasionally see them, but tonight we're going to hear about underwater drones, and so that's pretty exciting. And we have Phyllis Stabenow, who works with NOAA's Pacific Marine Environmental Laboratory. She is a physical oceanographer of great renown, so I don't know how much I need to go into it, but given that, and I will turn off this doorbell here, which I meant to do. Let's see, there. And tonight we're going to hear about underwater drones. So with that, let me fire it up for you, Phyllis, at this end, and we'll get underway.
Okay. So off we go.
So off we go. Welcome, Phyllis, and we can't wait to hear about what's going to happen off Nome shores. Take it away. Thank you so much.
So good evening, everyone. Gay has been telling us how good the weather is. So I'm in Nome, so I'm very appreciative of you guys deserting the nice weather outside to listen to this, at least those of you in Nome. So I would like to present today some information about a new piece of technology that we are beginning to use in the Chukchi Sea, or sorry, the Bering Sea, and eventually the Chukchi Sea. We're planning to deploy the glider in the northern Bering Sea this year. And so I'll start with kind of just a brief introduction of the project, and then give some information on what led us to develop this piece of technology. And then some information about the glider, about what we hope to do this year. Next. And so OMAO, who manages the NOAA fleet, has funded this project. And the goal of this, as I say, the Oculus Glider has been under development for 5 or 6 years, but it's been experimental. And so this funding is to help move it from experimental to operational. And that means that we would hope in the future to be able to deploy this every year, different places, but as we need information and what's happening, observations, etc. Our goal would be this would become a regular part of our deployment, similar to the moorings and the cruises. So there's multiple people on this project. It ranges from NOAA, engineers and scientists, to university scientists, including Gay. So next slide. So I know this is being developed. EcoFoci is going to be the group who will run the glider, hopefully, if everything goes right. And I think you know that EcoFoci's goal is to study the ecosystems of the North Pacific, Bering Sea, and Chukchi, and to improve the understanding and share this information with managers and stakeholders. Next slide. So FOCI has been in existence for 30 plus years. This is a slide that Heather made, and what it shows is where our CTD observations, and our moorings have been done over about a 30-year period. Everything from the southeast Gulf of Alaska all the way up into the Chukchi. Included in this is the long-term moorings of M2 of 27 years, M8 in the far north, which is almost 20 years now. And so we have a long history of observations, but to continue the observations and do well with them, we have to add new technology all the time. And I think we're very fortunate as scientists of where we're making these measurements, because technology has allowed us to make things that when I started, I never dreamed we would be able to make half of these observations. So anyway, so next slide. Okay, so this is a satellite image of the ice in March. Does this work? Yeah. So you can see the ice edge. The winds are kind of out of the northeast. You can see thin ice to the south of a lot of the areas. Here's St. Matthew Island, St. Lawrence. And so this is kind of just to kind of introduce you to some of the satellite images. So ice is critical in this system, and it really does set up the structure of this ecosystem. Next slide. And it's been changing rapidly. We're getting extremes of ice extent. For instance, in 2012, this is April 1st, 2012.
Hello, Geisha Phil.
This was the most extensive ice in the modern satellite era, which began in the late 70s. It covered the eastern Bering Sea shelf, it persisted, etc. Basically, 6 and 7 years later, we had the lowest ice extent. So you swung from this very extensive ice to very low. You can see 31st of March. Not only is the northern Bering Sea have limited ice, you can see in the Chukchi that there is just north of Bering Strait here, you can see open water there too. So it's interesting how much extreme you can have in these recent years. Next slide. So these slides pictures have all been related to ice extent. Another component that's really important is ice thickness. We deployed on the northern Bering Sea shelf, just south of St. Lawrence here at a M8 mooring, an instrument that measures keel depth. And so this figure down here, the black line is the daily average ice thickness. The instrument measures every second. It sends a beam up, a reflection, and you get the depth of the keel. And so that daily average is shown there. It's as much as about 2 meters of the keel. But the red line is what is the maximum keel depth. And the bottom of these ice flows are very jagged. And you can see that it's in mid-March that the maximum it was 20 meters. This wasn't particularly surprising. If you deploy your moorings up there and they go above 20 meters from the surface, if the floats go too high, we have lost moorings that we made too tall. And so if we keep them at 20, we've done very well not losing them. So it's not surprising, but this is the extremes that you can see of ice thickness, or really keel depth, not quite ice thickness. And so it's, there's changes in this. We're seeing some changes in the Chukchi Sea where we've had these type of instruments, the average depths. And so ice thickness is a real important component here. And thick ice takes a lot longer to melt than thin ice. Next slide. So let's go back to ice extent. The figure on the left is maximum ice extent on selected years. You can see the blue line is 2012, and you can see how much more extensive its maximum range was than the other set of data. And then 2018 is the solid red line, and you can see how low that was. That was maximum extent in 2018. So when the ice comes over these sites, it melts and it cools the water column. You know, in the vicinity of St. Matthew Island, the ice comes down. If you look at 70 meters of water, it takes about 10 days for the ice to melt and cool the whole water column down to minus 1.6 or thereabouts. It melts about 1.5 meters of ice. So yeah, it's very efficient way of cooling the water. It also brings fresh water. Yeah, the ice doesn't have much salt in it, so it freshens the water also a bit. But the big thing is you've now cooled the bottom of the water column, and that is important in structuring this system. On the right is the boundaries of the water column, the bottom of the water column, that's less than 2 degrees. So you can see 2012 had a very extensive area that was less than 2 degrees. And 2018, it was almost non-existent. This area is basically called the cold pool. And you know, how you define it varies a little bit, 0 degrees or 2 degrees, that type of thing. But this particular plot was with a definition of 2 degrees. Next slide. So on the right is all of the cold pools that have been collected or measured by the race groundfish group. The one problem with this set of data is it's summer data. And so it has a very, you don't see the evolution so much as what it is in the summer. The cold pool is very important. It provides a corridor for Arctic species, Arctic cod, crabs, etc., because they prefer the colder temperatures. It produces or provides a refuge for a number of young of the year, particularly pollock. And then it always has provided a barrier for subarctic species like pollock, Pacific cod, etc., because they prefer warmer temperatures. And so they tend to stay on the outside of it. Next slide. So this is just 4 years of data that measurements were made that far north consistently. The colored part, the yellow, purple, etc., that basically outlines the shelf, the Eastern Bering Sea shelf. The purple is how much walleye pollock were caught in the nets in those areas. The pinkish thing is the cold pool. This cold pool was defined as less than 0 degrees. But what you see in 2010, which was a relatively extensive ice year, nice big cold pool, and all of the pollock are on the outer part of the shelf, seaward of the cold pool. 17, 18, and 19, we're now changing this system. And what we're seeing is the pollock is spreading more across the shelf. By the way, the Pacific cod have almost identical patterns. 2018, their spread, you know, makes fishing a little bit harder when all your fish are on the outer shelf. It's easier to catch them when they're more spread out. It takes more time and effort. One of the big items is that you're now seeing these pollock in the Chukchi. The Russian fleet fished on them in the Chukchi a couple years ago. And so it's a real change in range extent for these animals. Okay. So next, Gay. Okay. So those two things were influenced by temperature, but this is another major thing that ice does, and it's the timing of the chlorophyll bloom. On the left, lower plot is across the bottom is the day of ice retreat. So, day 100 is in April. On the right hand or on the left axis is the timing of when you saw the chlorophyll bloom. This is all at M8, which has a fluorometer at it, so you can measure timing. And on the right at the bottom, you can see the time series of what a chlorophyll bloom looks like. And so historically, you can look up the dashed line or up from 100. The ice retreats on day 100, and several days after that, you see chlorophyll bloom. That's ice algae. The ice algae falls to the bottom and supports the benthic community. 2018 and 2019, there was no ice algae bloom. The timing of the spring bloom was late in June. And so it's a very, very, very different ecosystem with this delay in the timing of the bloom of all the plants that feed everybody else. So go ahead. Next slide. Okay, this is the kind of one of the last of these. This is some work of Catherine Burchalk. She uses passive acoustics to listen for whales, which are real chatty and like to talk, so you kind of know where they are by just them talking away. And I want to look at just two parts of this. If you look at the beginning, September 2012 to September 2013, the blue line is ice. The percentage of ice cover, and you can see on the right hand what the scale is. Basically, it's 100% ice cover within 20 kilometers of this site. And what you see is the bowheads come south, the ice comes down, they continue south and go into the Bering Sea or even further. The ice retreats, they return and move north, and you have the northern Bering Sea there. Same type of pattern. 2012-13, the winter was an extensive ice year, so it was cold and you had pretty good ice. And you can see all of the, as you go across here, a lot of these have this pattern of the bowheads going south, continuing south when the ice gets big, the ice retreats, and the bowheads come back. But the big thing in the winter of 17-18, unfortunately, the northern Bering Sea mooring failed, but you can see in the Chukchi that reduction of ice and the likely reduction of ice thickness resulted in the bowheads remaining in the Chukchi all winter. And this is the first time that this has been seen. And this is a direct result of the presence of ice and the ice thickness. So what we're seeing is all kinds of changes here as we're going through this period. And some of these we do quite well with the moorings, but these are single points that we're making these measurements at. And to really understand what's happening, we really need to extend our measurements. So next slide is from some work that Rick has done. This year, 21-22 was, Rick called it a wild weather, winter. I kind of just called it strange, but it was cold. The ice, it was very cold in November, very windy. So if you look at the plot on the left, the light gray guys are how much ice, the aerial ice extent every year. The dark black line is the average of all those years. And the blue one is 2021-22. So you can see ice arrived early. It's pretty extensive, nicely grew up above average. And then there was an ice retreat in March. And that's not unusual to have this ice retreat, but what's unusual is what's shown on the right hand is it wasn't that the ice was just blowing north and piled on itself and sat there. It disappeared. The ice was low. I mean, there wasn't a lot of it. And it was a real shock to many of us. I know Rick said it in his presentation 2 or 3 weeks ago, but I was shocked that it just disappeared. So why did this happen? And to begin to answer these questions, which are in part due to the changing system we're seeing here, is we need data, and we need to expand the database. So these are the type of things that have pushed PMEL to try to develop new instrumentation. And there's a number of things we've tried, but here I was going to talk about the glider that has been developed. Next. Okay, so this is called the Oculus Glider. Shown here is the glider being deployed from the back of a boat. You can see it going in the water here. Clearly, it's unmanned. It's relatively easy to deploy if you have the right boat, etc. It's a nice thing. It collects data. The price is much less than a boat, etc. Next slide. So this particular glider was designed for 3 things. Number one, it was designed to go in shallow water. Similar like the Bering Sea or the Chukchi Shelf. It was also designed to carry a heavy payload, heavier than most of the or the other gliders that you can get offline. And that's because, as I say, the new instruments, the new technology we have is just remarkable what you can measure. And it was important to have a glider that can have a heavy enough payload that we can measure not just the normal things that it has now, temperature, salinity, fluorescence, oxygen, PAR, and depth, but other things like nitrate, hopefully maybe in time some type of eDNA, genetic type sampling, certainly photos, etc., cameras, sorry. And so, so it was important to make it so it had a pretty heavy, payload that it would carry. It's also a pretty fast glider, faster than most of them, for a couple reasons. One is to cover more area, but also it allows the changing, so it dives, and you want to get as close to the bottom as you can as you change direction. The deep ocean ones that dive, they have a pretty slow change of vertical direction from going down to going up. Next slide. So this actually is my favorite picture of the glider. It's not real, but I think I like the sun at the top, etc. So our goal with this project is, number one, to move forward to develop it so it works well in the Bering Sea and the Chukchi, and that we can add it to our sampling scheme. In addition to having moorings and drifters, shipboard measurements that use this type of an instrument, and we own 4 of them at the moment, to sample in remote places that we don't have ship time to do and no one else. The other thing that's important is we want to partner with communities, so we don't need to have a large research vessel doing the deployment, but have a broader community partnership on this. And so this, the moorings give us a point. This would give us the spatial grid around that point, or examining a frontal structure, that type of thing. The other thing is it provides real-time data. And as the models continue to advance and develop and they assimilate data, they need real-time data to assimilate so that the predictions of ice retreat or other things can be made and can be made reliable. So those are the goals of what we would like to do. Next slide. So this is just a quick sketch of how it works for anyone who hasn't seen it. It starts on the surface. It talks to the satellite and sends back whatever data it has. It dives downwards. As it senses the bottom, it quickly changes direction, comes back to the surface, and then can transmit the data again. Usually it does 2 or 3 dives without transmitting data. The other thing it does when it comes to the surface is it looks at seas exactly where it is, because how it moves through the water, it has a trajectory of where we want it to go. And with the currents and that type of thing, it doesn't exactly stay on the trajectory. And so it needs to correct that. So it gets its position. It says, okay, I'm too far east or west, and it changes how it dives a bit to head back to the line of the trajectory it's supposed to be going on. Okay, next slide. Okay, so we deployed a precursor of this particular glider in 2017, I believe. This is results from a paper by Carol Ladd. And we deployed 2 gliders. And what we wanted them to do was go up the 70-meter isobath. And that isobath is kind of on the middle of this gray area, the broad eastern Bering Sea shelf. And we wanted it to go as far north as the mooring I discussed earlier, M8, turn around and come back down and be picked up somewhere between St. Matthews and the Pribilof Islands. So it succeeded in doing that, but we would like to talk in the left-hand figure, we'd like to talk about this about 300-kilometer, 150-mile part where it goes right near St. Matthew Island. So if you probably can't see it, but if you could, there's 2 trajectories there of the glider. One is the trajectory of it going north, and the other one of it coming back south. The black dots are where we do CTDs traditionally. But anyway, on the right is what it looks like. And this is temperature. On the left-hand side, that's the south. On the right hand is the northern part of this trajectory. Yeah, it's very nice and flat at the beginning and at the end. But as it goes past St. Matthew Island, you see a lot of dips of the in the mixed layer, that type of thing. If you look at any of them very carefully, that's what you get in the bottom. And this is salinity as opposed to temperature. You see the very salty water on the bottom, the very fresh water on the top, and in the middle you see an eddy-like feature. It's subsurface type eddy. It's basic, is pretty well mixed in the center, and and it's it's an kind of an average of the fresh water at the top and the more saline water at the bottom. Next slide.
Phyllis, this is Gay. I just have a question on this colorful thing. So the top one is the looking forward as you're going along the shelf break, where it says northbound?
So the left-hand start is at the very southern part of this little rectangular map. And so it dives, it makes about 2 dives a kilometer. And so you get a lot of data, and it measures, this top plot is just temperature. And so you can see the warm 10, 11 degree water on the top, the 0 degree water basically on the bottom. And it just goes back and forth. And so you map the shape of the bottom and everything. But as you get close to St. Matthew's Island, it becomes very ragged and very up and down. And then once you get past St. Matthew's Island, it now becomes very flat on the bottom. So it's a real nice image of that. And like I say, the bottom is just salinity to show what the salinity structure is on one of these eddy-like features. And
great, thank you very much.
Yeah. So the next slide, expands this a little bit. So we took the trajectory and we put it on top of a satellite image. And this satellite image was chlorophyll. This was a chlorophyll image basically around. There wasn't much happening anyplace else except for around St. Matthew Island, which you can see in white there. And there were 3 on the right-hand side. This is now density, which is how dense the water is a combination of the temperature and salinity. And you can see kind of these 3 eddy, we call them eddy type features. And each of those, and the map isn't great, but each of those are in one of these lobes of high chlorophyll. So, you can, they're meanders or eddies, and that's what you're seeing. So you now have a real detailed show of that. At the very bottom of these 3 smaller panels, this is chlorophyll again, as measured on the glider. And you can see how the chlorophyll both comes to the, it's a bit below the surface, right below the surface mix layer, but in the eddy region, it comes to the surface. It also is entrained down below. And so there's a lot of chlorophyll right in this region. At the same time, or actually it was a few weeks earlier, we did CTD stations, and they're about 10 nautical miles apart. And each of those eddy-like features, each of them had high zooplankton in them. So these features are kind of a mechanism. It's not that everything around the island has a lot of chlorophyll and a lot of zooplankton. They're associated with these small scale mechanisms or things, and they provide a lot of information, more information than we got from the CTDs. If you towed a vehicle behind it, you'd get similar information. But these gliders can be used to explore a lot of a different type of things. On the left, you can see the glider. That's the Dyson in the background. And so this is, we deploy these, or we have this year, we deployed them with research vessels. And that's one thing we'd like to get away from, of having to commit, the Dyson or other vessels to deploy, recover, deploy, recover. If we really want to make these effective in in sampling, etc. So, okay, so the next slide. Okay, so what are we planning on doing? So the funding we have is to deploy 2 gliders this year, each of them for about 30 days is our plan. Hopefully we'll succeed in that. But also part of this plan is to partner with a community and utilize smaller community vessels to deploy, say, the glider. The glider goes off and does its business, and then, you know, help to recover it. Ideally, you'd like to maybe sail them into a harbor, but that's not really feasible yet. So this year, we'll have 2 deployments, 30 days each, and we want to do it in this general kind of dashed red area. And we would be able to make multiple observations, in the sense we'll have a spatial observation, in that we'll do multiple lines, either north, south, or east, west. We haven't decided exactly how to do it. And just look at the structure of this. These will be done in the summer. Eventually, we would hope to be able to do them in the fall before ice arrives, but certainly to give us later observations, or in the early spring before we have anyone has an opportunity to take a vessel up there. In my very long-term dream is to be able to fly these under the ice and make measurements under the ice and see how, how the system changes and that type of thing. So in 2023, we plan to deploy all 4 of the gliders, 2 in this northern Bering Sea and 2 in the southern Chukchi. And so we're moving forward as best we can with our plans. COVID has, delayed certain things, but that's our plan. And so the other thing is, I want to comment on, the previous deployment was in the 72 meters of water. This will be in 40 meters of water, at least in part. And that's a real test of this type of technology to see how well it handles, because it takes more energy for it to dive, rise up more often. If it's shallower, it's going to go up and down more often. So that means it has to pump the liquid that puts the weight in the front or the back to cause the diving or rising. So next slide.
Having some technical, that may be it. Let me.
So, okay.
You have, yep, I am trying, but it doesn't want to. Let me see what the date is. Okay. Hang on, We'll get it back on.
Yep.
Don't know what that was all about.
It was going too well. It had to do. So there's an opportunity here. NOAA's acquisition team will be seeking competitive offers related to the deployment and retrieval of the glider. That document, or that competitive offer, will go through sam.com. Anyone's interested in that, they'll have to register at sam.com and take a look at it. And so once this is submitted or whatever to Sam, Gay will also get a copy of it, and she can advertise or distribute it locally to help out in getting a vessel to help us out with this. But as I say, there's 2 parts of this thing we're trying to do. One is, develop this technology to improve the measurements we need to make. to better understand how this system is changing rapidly. But the other is to partner with local communities to do this in a more effective and more efficient way. So next slide. Which is, yeah. So thank you very much for coming and listening. And are there any questions?
All right, thank you, Phyllis. Thank you very much. So I know that I've got a couple questions and I'm sure other people do. So while you're thinking of your question, now is the time to, in good straight science form, throw some love down there in the chat box for Phyllis, because it's never easy being a public speaker. And obviously I even Zoom bombed my own presentation since I had a call. I thought that was somebody trying to get on. But anyway, thank you very much, Phyllis. And you actually had, there was a question in the chat from Melanie. Under ice, would the glider get stuck on ice keels, or are they designed to bounce off of objects like a Tesla as they glide?
One of the real problems is the ice keel depths. And so it wouldn't be something you could do in the dead of winter. Simply because the bottom, there's deep keels under all of this ice. But that's one of the things. A harder thing is how can the glider find its way around under the ice? And there's a lot of technology that people are beginning to do this. And it's just that what's happening under the ice really matters. And we haven't had great observations, or observations have been limited. So, yeah.
Regardless of the dogfight in the background. Thank you, Phyllis. Anyone else have a question? I know I have a question. That is, how are these things powered? It's not coming up. Are they solar? I mean,
no, how it's is it powered by batteries. It's
okay.
Purely, yeah.
All right, so that's the 30-day length of that limits the.
Yep, it does.
All right.
Yep,
that's interesting.
The fewer times you go up and down, the fewer samples, measurements you make, the longer it can go out for. But if you're greedy, like I am, and you want to sample often and go up and down a lot, you have shorter durations.
Batteries and a buoyancy engine with oil, no motor. Okay.
Mm-hmm. So yeah, so there's oil in it, and the engine pushes the oil to the back or to the front, and that determines its diving. So it goes down when you push the oil to the front, and then it comes back up as you push it to the back. And so that gives it, the buoyancy, that type of thing. Heather can explain it better. I think it's another remarkable piece of technology.
Heather, do you want to take a crack at that? And Rick, I see your hand up. You'll be next.
Hi, everybody. This is Heather Tabasola. I work with Phyllis. No, I think Phyllis explained it pretty well. The thing about the glider that makes it so unique in the design is the way in which that buoyancy engine was made, because it allows it to make those more rapid changes that other gliders just can't. And so basically, like she said, it will use a pump, and it allows it to move, change that buoyancy and move forward, but it just moves it faster through the glider so that it can change it. So leave it to an engineer to describe it better. It goes up and down faster, and it does what we need. So
I have another question on that, but we've got Rick and Dean, and also a question in the chat. Go ahead, Rick.
Yeah, thanks, Phyllis. Really interesting presentation. Thanks for taking the time. You may have mentioned it, and I might have just missed it, but is there a timeline for moving this from beyond experimental to something like operational?
2 years. we did what's called a transition plan in NOAA, which is the plan of how to make this operational. At the moment, it's experimental, and we hope to move it to the level where it's not experimental. And we have 2 years funding to make that movement. And so, yeah, and we've already had plans for, so we sail this year, and then we'll sail next year. And we're already thinking of different sampling that we need for different places. And I think as we see the changes that are happening in the Bering and the Southern Chukchi, I think, discussions of what we need to measure to better understand, to improve the models and to help predict how the ice disappearance this year, like you said the other day, Rick, was shocking. I thought we would have fat ice well into April in the north. And I think it is just, I don't quite understand how such cold water and such cold winds could allow that retreat or that disappearance of ice so rapidly.
Okay, great. So a couple years. So looking forward to that. Thanks a lot.
Yeah.
All right. Dean, we see you with your hand up. Go ahead.
Yeah, two things, Phyllis. First of all, nice talk. Really appreciated it. The first thing is an FYI. The Norseman 2 will be running the Spanberg Strait with CTDs twice during the summer, roughly the 19th of July and the 17th of August. If any of the CTD information can help you, Bob Picard will have all that information.
Yeah, well, thanks, because we'll also talk to them in case the glider is in those regions at that time. So it'd be a real shame if it and the CTD tangled and we destroy everything. So thank you very much for that information. They're going to be in Spanberg then.
Yeah, as usual, you're on top of it, so appreciate that. The other one goes back to your sea ice keel slide, and you were looking at the variability in ice keels moving across your area. A lot of people think of ice fields when they look at these maps as somewhat static. Do you have any way of moving or seeing the velocity of the ice moving itself from this device?
You can. There's two things you can do. One is you can set the ADCP, a companion ADCP, up on bottom track. But the other thing that Peggy and I did in the Chukchi is we looked at the satellite imagery, and you could see certain flows going right on top of our moorings up there. And so we calculated how fast the flows went, and we pulled up the ADCP data and did correlations with that. And if you have solid ice, if you have a big ice sheet, forget it. But if you have chunks of ice, it's correlated with the speed of the currents. I suspect it's also correlated with the winds. But in the Chukchi, the winds and the currents are so highly correlated, it'd be difficult to separate the two. So we used the currents, because the currents, we had hourly data and we thought that was more useful. So, but yeah, if you combine all of your data together, I think you can begin to, and satellite imagery, I think you could begin to see how rapidly they go, because the time series gives you, well, how rapidly does the keel go by, but it doesn't tell you how thick the keel is. If you can figure out how fast the ice is moving, then you can translate that into the width in meters of the keel. And that, I think, is, you just have to integrate everything you have to get those numbers, I think.
Oh, really appreciate that. But I'm going to tag you with one more thing then, going back to Rick Toman's slides, showing all of that open water right along the coast. There were strong, very strong northeasterly winds at that time. Is there a chance that that's a reaction to upwelling and it just blowing the stuff off?
Yeah, but I still would, the water was so cold. I mean, it had been covered in ice for 4 or 5 months. And so it was frigid, cold. And it just seemed like those open areas hung around for longer than I would expect. And I mean, the water had to be minus 1.6, 1.7. We'll know, we have moorings up there. So I'm hoping that they will tell us a bit of the story of what we had. We also have an instrument up there that measures keel depth, but I'm not sure it survived. I think the battery might have run out before this time of year, March of this year. But yeah, we'll take a look at what we have. But yeah, it just seemed like usually, you know, the winds blow from the north and you pile all the ice up, and then the winds may change in direction. But yeah, it surprised me how little ice there was after such a cold period, cold winds, cold water, etc. And it lasted. And so I don't know. I think looking at the data and everything, I think perhaps, you know, and a lot of people have measurements up there, and together I think we might look at, and you could be right. It could just be that the winds were so strong that they opened up that the thicker ice was all blown out where temperatures were warmer and it melted it. And that's what we saw.
Yeah,
But
I just know,
never.
I just know
Go ahead.
earlier this year off Utqiagvik, they had strong easterlies that opened up the water up there too
Yeah.
but it was a shorter time.
Yeah.
Anyways, thanks. Appreciate it.
Yep.
Thanks, Dean. There is a question in the chat. Can you put a hydrophone on the Oculus Glider for eavesdropping on whales?
That is a goal that we've looked at. You have to be a little bit careful because these things can make noise. I mean, as they go through the water, they can make noise, and how that affects the quality of data the hydrophone makes. For instance, we looked at putting hydrophones on the sail drones, and they were too noisy. The sail drone going through the water was too noisy, and so we'd need to do something different. I wasn't heavily involved in that, but I do know that was the result. And so that's the trick. I think the new hydrophones, the old ones were huge things that weighed a lot, but there's some new hydrophones that are much lighter in weight and that type of thing. Yeah, our goal is to look at, since it can carry a decent payload, is to look at a lot of this technology and see what else we can add to it to better understand the whole ecosystem.
All right. Any other question for Phyllis? Now, I was joking around a little earlier, but given this summer, I hope that for you guys are going to put some kind of indicator on there, because we have a lot of people boating, especially in the area you're going to be in. And given this summer may be unusual, certainly it's unusual right now, our situation geopolitically, are you going to put a big old American flag on that? Because I can, and people may laugh, but I can tell you that if this summer, if people do not mark their equipment, it could be
So
challenging to get it back.
Yeah, exactly what we put on it, but we agree we need to label it, especially if someone finds it on the beach. It'd be nice to get it back. But yeah, and we also need to advertise that some pictures, this is what's going to be out there, etc. And
That's good.
yeah,
That's
so
good.
yeah.
Yeah, and the fact that you're doing all this to better the models, I appreciate that. And you were saying that you were extending instrumentation, and I also look at it as extending communications. We have you here tonight, which we're learning about this project, and I think as science moves into the Bering Strait region, I think that more and more that collaborative nature is going to be nothing but good as far as people talking to each other.
Yep.
And I think that's
Yep.
going
I mean-
from a wide open ocean in the southern Bering Sea to really a place where you sort of run out of ocean up here, and we have such great.
Yeah, the partnership part is really, really important, both in identifying what needs to be measured, but also in for instance, modeling, I think, is real-time modeling. I've always thought one of the great things that models, if we have the right observations, could do is could predict perhaps when the ice, the land-fast stuff might break apart. I mean, there's a number of things of observations that modeling could help with a lot, and observations are needed in the modeling to predict. Is there going to be a law of Pollock in the northern Bering Sea, or Pacific cod, or whatever? The models are becoming more and more sophisticated. While they don't assimilate, or at least the models of the group that I'm working with, assimilation isn't there yet, but it's a goal on the table, being able to do that, so to make better predictions.
And certainly using the data sets that people in this region have in their regional and local knowledge are as soon as those connections are made, I think that would help very much, maybe understand better. So every little bit helps. And then I have my last question, unless someone else has a question, and it's actually has nothing to do with gliders, but it has to do with physical oceanography. And right now, because I was thinking, man, we have Phyllis right here, and she's going to take a question. So we see in Fairbanks that they got a ton of moisture, record breaking. We learned that recently, that it was, I don't know, we still have Rick Toman on. It was like 400 times or some, is that right, Rick? It's like 400 times what you would normally get for the interior. And all that water is in snow and ice, and it is headed our way in some, if it was record breaking in the interior, it's probably going to be a very serious melt out on the Yukon. Well, the Yukon is a terminus just southeast of Nome. Any idea what that amount of fresh water output that is potentially coming our way? Not probably happening yet, although our rivers are starting to get holes right through the ice in them, and we've got runoff on top. So we're melting out really nicely. Any ideas what we should expect with having that? I don't even know. I mean, that just sounds like we should expect a giant bolus of fresh water.
Yeah, well, we've been thinking about what the Yukon is going to dump there too, because that water goes over the top, so you end up with a fresh lens, and that can cause problems, from my narrow point of view at the moment, of the glider, because the glider has to, if you have really fresh water at the top and more saline water, it has to go through that interface to get to the surface. And fortunately, we have the buoyancy engine to force it through. But we've been looking at those numbers. And I think it's going to depend how windy it is, how much mixing down you get. It's going to be fresh. And the question is it coming down as a lump, or is it going to dribble down? And that I don't know. River stuff is not something I've ever looked at, of how rivers flow, how rapidly they'll drain an area, etc., etc. So I think you'd have to maybe talk to Rick or one of those.
Well,
guys.
Rick's commented in the chat box, and Rick, I don't know what SWE is, but SWE in the upper Yukon Basin, including the Tanana, is 4 to 5 times normal, 4 to 500% of normal.
So that SWE is snow water equivalent. So the amount of water in the snowpack, that's what's going to be coming to Norton Sound here, in May and early June. And in the Tanana Basin, it's by far the most water that will be coming down. And same in especially the Yukon portion of the Yukon River drainage is also far above previous records. So there is going to be an immense amount of water coming into Norton Sound in May and June.
And I
Yeah.
think actually there was like a warning on National Weather Service today, or a notice that the interior, is that right? Rick tuned off, but you're going to get some sustained high temperatures, and they're warning people already about that. Is that?
Yeah, we've got this record snowpack, and it's been mild now. I mean, mild as in near normal, which is a big change from what it was. So we've got rapid snow melt now. Normals are now, in the 50s and 60s in the eastern interior for highs, and that's what we have. So water is moving into the rivers now, and it's going to be a prolonged process. First, we'll have the breakup and the threat of ice jam flooding, but that's just part one. Then we've got all this water that will take several weeks to work its way down the river, but it's all going to wind up in the Bering Sea.
Yeah.
Thank you, Rick.
It doesn't sound good. I mean, up here in Seattle, when we get rain and heavy melt in the mountains, the rivers here freeze, not freeze, overflow also and flood. And so it doesn't sound good. That much water on that flat of an area is I don't know.
So as far as physical oceanography, having a giant dump of fresh water just southeast of us, that will, from what it sounds like, you'll have a big freshwater lens potentially on top, unless we get some storms and really mix it up.
So for our measurements, I'm really glad to know that because we gave the historical vertical structure in Norton Sound and around there. So using that as a density, if it's going to be double that or whatever, I think we're going to need to, we'll probably be talking to you guys, because if the thing can't make it to the surface, then heaven knows where it will go. And so we need that. But historically, where we're trying to run it, it's far enough away from Norton Sound that it doesn't get an extreme lens. But if the winds are in the right direction, you could begin blowing those type of lenses around. I don't know. I hadn't realized how much water had fallen on the interior.
So, well, thank you, Phyllis. And we're all curious to know how that is going to pan out. So I didn't mean to put you on the spot, but that is, what does that mean for fish and our water movements and things like that? It's going to be very interesting. Temperatures.
There'll also be a real signal going into the Chukchi. That much fresh water would be a real signal in the ACC. So
the Alaska Coastal Current. Yeah. So with that, any other last minute questions or comments? Thank you all so much for coming.